In this work we will present a framework to learn optimal controllers by using a supervised learning technique that leverages dynamical motion primitives, and how to make it more sample efficient. First, we will state the motivation of the problem and give the necessary background for understanding our work. Next, we present the proposed technique, and after that, show some numerical results illustrating the potential of the technique. In the end, we will conclude this work with the summary of our results. Real-time computation of optimal control is a complex and challenging problem. However, researchers have proposed learning techniques that enable the online usage of controllers, even if they are suboptimal. One successful approach in this area is the optimal motion framework, which is based on encoding optimal solutions obtained by numerical solvers and dynamic motion primitives. Estimating the suboptimality of learned solutions, however, poses its own difficulties. This paper introduces a novel method to estimate the error associated with these solutions. By leveraging this estimation technique, it becomes possible to design more efficient sampling schemes, allowing for better utilization of available computational resources. Dynamical motion primitives, or DMP for short, are second-order differential equations given by equation 1, where its forcing function f is a sum of n Gaussian basis functions. The center points and widths of these Gaussian functions can be computed as shown. DMPs can be used to generate trajectories that are qualitatively similar to a trajectory demonstrated to a mechanical system. To achieve this, we measure the states and the time derivatives of the states of the demonstrated trajectory to learn the forcing function f. More precisely, we solve the optimization problem in equation 2 to obtain the weights omega that defines each component of the forcing function. For more details, the viewer is referred to the paper and the references therein. After learning the weights omega from a single demonstrated trajectory, it is possible to use the DMP to generate new trajectories that are qualitatively similar to the demonstrated trajectory, but with different ending points. This new trajectory can be obtained by integrating the differential equation using the same parameters and forcing function, but now with the new different goal. In other words, a DMP allows generalizing a demonstrated movement to similar trajectories that have different terminal endpoints. Now, we introduce how we can use DMPs for learning near-optimal control solutions. Given an initial state x0 and a terminal state xf, we numerically solve the optimal control problem and encode this optimal solution in a DMP. If a new terminal state is close enough to the original goal, we use the DMP to generate the solution of the optimal control problem using the new goal as the new terminal state. To get the optimal control associated to the optimal trajectory, we replace the optimal trajectory in the system dynamics and recover the optimal control from there. In particular, this is always possible for mechanical systems. Assuming that optimal solutions with close enough terminal endpoints have qualitatively similar shapes and close values for the objective function, the DMP will generate a near-optimal solution. It is important to mention that while this assumption seems very restrictive, it has been verified in practice for some works that consider optimal control problems related to reaching motions with minimal energy and elastic robots and time-optimal maneuvers for quadrotors. However, even if we accept this assumption, it is reasonable to wonder how much the trajectory associated to a new fixed terminal point can deviate from the true optimal solution before becoming too different. If this situation arises, one can represent the new trajectory as a new DMP and utilize it to generate nearly optimal solutions with terminal states that closely align with this new trajectory. Nevertheless, this may require to learn a large number of DMPs. The main contribution of this paper is to propose a learning strategy that reduces this number based on a user-defined threshold of suboptimality. In the terminology of supervised learning, each demonstrated trajectory is a sample and we want to achieve a strategy that uses less samples as possible. To achieve this, we will propose a new method to estimate the suboptimality near the learned optimal trajectories. For our results, we considered optimal control problems of the same form as the equation 3, which are relevant in many motion planning problems in robotics. In what follows, we will assume that this optimal control problem has a unique solution for each fixed terminal state in a region of interest. Moreover, we will assume that the matrix-valued function Q is either identically 0 or a positive definite function, and that the matrix R is a positive definite matrix. In order to estimate the suboptimality of a generated trajectory, we will need to estimate the cost of the true optimal trajectory. To this end, we will get the cost of optimal trajectories by using the notion of the optimal value function, which is equal to the cost of the optimal trajectory that starts in the state x at time t. In the following we assume that v is differentiable. To assess the suboptimality of the new trajectories generated by DMP, we will also utilize lemma 3 from our paper. This lemma enables us to convert the original optimal control problem, described in equation 1, into an equivalent problem, where the trajectories are reversed in time, but the costs remain unchanged. In particular, the optimal value function of the backward time optimal control problem will be used now for estimating the suboptimality of the generated solutions by a DMP. By the assumption that the value function is differentiable, one has the following first-order approximation for the optimal value function associated to the backward time optimal control problem. The left-hand side of this equation is equal to the cost associated with the optimal trajectory that reaches the endpoint x'(f). The term v tilde evaluated at the state xf and time 0 is the cost of the optimal solution used to build the DMP at terminal state xf. It can be obtained by computing the cost of the optimal solution returned by the numerical solver. We will show now how to compute the derivative of v tilde with respect to x, which is evaluated at the new terminal state in time 0. Assuming the differentiability of the value function and taking into account the dynamics of control-affine systems, it is possible to prove that the optimal control solving the backward time optimal control problem is given by v star. Assuming that g is invertible, we can recover the derivative of v tilde with respect to the state along an optimal trajectory. In particular, we can recover the derivative from the associated optimal control computed by the DMP framework. We note that we can also recover partially some components of this derivative, even if g is non-invertible. For more details, please refer to our paper. We now summarize how to use the previous results to get first-order estimates for the optimal value function. First, we solve the backward time optimal control problem in order to obtain a backward time trajectory z and its associated optimal control input v. In particular, we obtain the value of the optimal control input which starts at time 0 at the state xf. By lemma 3, we can obtain the partial derivative of the optimal value function associated to the backward optimal control problem. We revert the solution using the transformation defined in lemma 3 to recover the optimal trajectories of the original optimal control problem. Then, we use the DMP to generalize to a new terminal state. This generalization can be obtained by integrating the differential equation associated with the original DMP, but replacing the original goal by the new goal. To estimate the suboptimality of the new trajectory, we use lemma 3 in the first-order approximation that was previously explained to estimate the cost of the true optimal solution and to compare it with the cost of the generated solution by the DMP. Based on this estimation, it is possible to design a cost-aware sampling algorithm that allows one to avoid relearning DMPs whenever the cost of trajectories near it is already good enough for a given application. For more details, the viewer is referred to algorithm 1 of our paper. To illustrate the application of our method, we consider following optimal control problem, where the terminal state is a varying parameter within the set in equation 5. The result of the estimation can be seen in this figure. In each graph, the abscissa shows the fixed terminal endpoint of the previous optimal control problem. Subfigure A shows the difference between the true optimal cost, the cost obtained by using the DMP solution, and the estimated value for the optimal cost for different terminal points. Whenever the difference between the estimated optimal cost and the cost obtained by using the DMP solution is above 10, we use a new DMP to encode the optimal trajectory towards this terminal endpoint. Otherwise, we keep using the previous DMP as long as the difference is below the user-defined threshold or the new terminal point is too far away from the DMP original terminal point. Subfigure B shows the error between the estimated optimal cost and the real value of the optimal cost. The maximum absolute error is given by 1.07. Subfigure C highlights the difference between the cost of the DMP trajectory and the real optimal cost. In this figure, the difference between the proposed sampling strategy and the naive uniform strategy can be clearer seen. The uniform sampling strategy needs much more samples, more than double of the samples required in comparison with the proposed sampling strategy. In this work, we developed a method to estimate the error between the cost of a trajectory learned by the DMP and the cost of the true optimal solution. This method was then incorporated into a DMP-based framework for optimal control, allowing for estimation of the optimal value in proximity to the learned trajectories. By utilizing this estimation method, a sampling scheme was derived to address storage limitations in applications like embedded systems, where reducing storage requirements is crucial. Thank you for your interest.